Not yet. Okay. And I will let it to Szilard to try to convince us that there is something which is better than deep learning. Please take the stage.
Hello. So I'm really glad to be here, especially that yesterday evening my connecting flight was cancelled. So I'm really glad to be here. So I have a little disclaimer. And I will start with deep learning. So probably many of you have seen those famous slides from Andrew Yang. This appeared a couple of years ago, and he's trying to say that deep learning is beating every other single machine learning algorithm. And of course, deep learning powers self-driving cars, and it's beating world champions in games. And of course, we are on the verge of AI, artificial intelligence. So I think the reality is a little bit less than that. So deep learning is great in image classification. There has been amazing results using convolutional neural networks. Also, LSTMs are pretty good in predicting sequences, and combined with reinforcement learning, deep learning had tremendous success in many virtual environments, such as games, where you can create infinite amount of data by playing machines with themselves. But I don't think this is AI yet. So, and I'm not even convinced that deep learning is really the path to general artificial intelligence. And also, most importantly, a lot of us work in businesses, and we do machine learning, and machine learning has been done in various problems in businesses for 15, 20 years. And for example, in fraud or credit scoring, marketing, manufacturing, telecoms, or insurance. And I tried deep learning in some of these domains, and it didn't really beat the state-of-the-art algorithm that we've been using for many, many years. So here I have some GitHub repo where I try to tune deep learning to beat other algorithms on a public data set. It's an airline delay prediction data set. And I wasn't able to beat with deep learning the other algorithms. But I think if you want to see which are the most accurate algorithms, we can look at Kaggle. So Kaggle has been organizing machine learning competitions. And there is this talk by Tianqi Chen, who's been in Los Angeles at my meetup. And he was saying that 2/3 of the Kaggles are won by using XGBoost, which is an implementation of gradient boosting, which I'm going to talk about next. And only about 1/3 of Kaggles are won by deep learning. So here's a little bit of correction to Andrew Yang's slides that I'd like to send him. So if you're working with structured data in a lot of business cases, gradient boosting machine actually beats deep learning. But for those of us who have been in machine learning and data for many, many years, this is nothing really new, and it's not really surprising. There are here 2 excellent papers that are not outdated, even though they are from 2006. So these 2 papers with overlapping authors have looked at many, many data sets, many algorithms, and different accuracy metrics, and has found that the most accurate algos are like random forest, neural nets, boosting decision trees, support vector machines, and it kind of depends on the data. But it's certainly not always neural networks. So this has been done on relatively smaller data sets. Since then, people have done similar stuff on larger data sets, myself included as well. And if I want to give you a glance at what algos you should use if you have a problem and you have little time to try everything else is probably for structured or tabular data. I would start with GBM, so random forest. If you have small data, you cannot really use GBM, so you should do probably some simple model like linear models. If you have large sparse data, this has been mentioned in the previous talk, then you should use probably a stochastic gradient descent on some simple linear model and also some strong regularization. And yes, if you have images, videos, speech, then deep learning is really the best. So this is like, it's a bit misguided. So actually, it depends. Also, if you have time, try them all and compare which one is the best for your data. Do hyperparameter tuning and also ensemble. So with ensembles, you can get even higher accuracy. And also, you can gain a lot of accuracy not by modeling, but by doing feature engineering. And in many problems, accuracy is not really the only goal, or not even the most important goal. So if you might need interpretability or fast scoring, and that can change all of this. So by now you can see that the title of this code was totally misguided, and just to make you come to my talk. But also, so recently, it's almost every use of the term AI is misguided as well. Now let's go to see what's gradient boosting. So I would start with decision trees. That's the basic ingredient. So decision trees are basically recursive partitioning of the input space. And then you end up with like a decision tree, which looks like this. You split based on variables, and at the end on the leaves, you have some kind of prediction. So the first boosting algorithm that comes from around 97 was AdaBoost. So AdaBoost builds several decision trees, and then the prediction will be the average of the predictions from the decision trees with some weights. And in each iteration, a tree tries to learn what all the other trees have missed. So you do this by upweighting the errors, basically. So the observation that has been mispredicted, you give them more weights so that the next tree will pick that up. The other algo is also around 98, 99, gradient-boosted decision trees. And this does something similar with the gradients. And if you want to understand the algo, you should look at this excellent book by Hastie and Tipshire named Friedman. Friedman is, by the way, the inventor of the GBMs. What about implementations? There are so many implementations of gradient boosting. And this guy has looked at a couple of them and tried to benchmark them. And if you look at this repo, there will be a lot of scalability graphs looking at the accuracy or the training time versus size of the data sets. And I will spare you the time, and I will just tell you basically the end results are that these three are the best open source implementations, I think. XGBoost, H2O, which Evan has been talking about, and Microsoft has open sourced recently package called LightGBM. And all this have R packages and Python wrappers as well, so it's very easy to install them and use them directly from R. You might ask, what about Spark? So Spark is really great for ETL, but for machine learning, basically it uses 10 times more memory. It's 10 times slower than all the others. So at this point, I can safely say that it's just garbage. Don't use it. It's just wasting your time. But I have big data, so I must use Spark. No, you don't. So I don't think most of us have big data. what I think most of us have access to big memory. So you can easily buy a lot of RAM into your servers, or you could use something ready from the cloud. For example, this instance I've been using a lot. It has only 250 gigs of RAM. That's been around for more than 4 years. Now Amazon has a 2 terabyte, and I think since I made the slides, even bigger machines. So actually big RAM is kind of eating big data. So you're much better off using, at least if you do machine learning, once your data is refined, it's usually small enough to fit in RAM at these sizes. So I took this benchmark and I took the best tools, which are H2 XGBoost and LightGBM, and I created another benchmark repo, which I Dockerized so that anyone, you can just easily run it, and it's more reproducible. So last time I ran it in January, LightGBM, if you care about the fastest runtime, then LightGBM is now the fastest of these 3. If you have a GPU, now GPUs rage because of deep learning. These tools have got GPU implementations recently, so this implementation are really new. So all of them, they are from less than a year ago, and it seems that XGBoost has the best GPU implementation. That's the fastest. Since this is an R conference, I have to throw in some R code. So it's really easy to use any of these tools. It might be too small, but basically what you need, read the data. For XGBoost and LightGBM, you do need to do some encoding, for example, one-hot encoding. And then the training is just really one line of code. It's this, and then the prediction is another line of code. So it's super easy to use these tools. If you care about production and you want to do real-time scoring, then I think H2O is the best. So they make it very easy to create a web service with REST API in just a few lines of code. I will tweet the slides, so don't worry if you don't catch everything here. So GBMs have a lot of parameters. The most important are number of trees, depth of the trees, and the learning rate. This is how you combine the trees, one after another. And something important is also early stopping. So you want to do early stopping because GBMs, if you overtrain, the accuracy on a test set or in a validation set actually starts to decrease because you are overfitting. So you have to stop somewhere. All these libraries, the best ones, they have early stopping parameters. There are tons of tutorials about how to tune the hyperparameters for GBMs online. So just Google for GBM tuning tutorial. And then what you can do, you can do manual tuning, you can do grid search, or you can do random search. I would recommend random search. That's computationally the most efficient. If you want to know why, there is a paper by Bengio here. If I post the slide, you will see it. And also there is another excellent blog post explaining that 2x random search beats even the most sophisticated Bayesian methods. So you just need 2 times more computational resources, like run it twice as long or have twice as many CPUs. And then do something simple like random search rather than some very complicated Bayesian optimization. I've been playing a little bit with random search in this repo GBM tune. So you can, if you look at this, you would see what kind of parameter values you can choose and which really matter. And then you would think that if you have more core, all these are multi-core implementations, you would think that if you have more cores, it's better, but it's not necessarily. So if your CPU has hyper-threaded cores, that actually slows down. You're better off just restricting your process in Linux on the actual cores. Also, if you have more than one CPU in a server, that actually really slows down some of the libraries. So there is this monster 128 core instance on Amazon. On that, it runs slower, like 5 times slower than if you just run it on a few cores. So you kind of have to know what you're doing. And of course, machine learning is a lot more than just training as fast as possible. It's also deploying the models and using it in production. And I put together this table. I never wanted to throw in all these comparisons because then all these developers will hate me for some reason. But here you go. If you kind of want the fastest training with CPUs, then LightGBM. If you want the fastest training and you have GPUs, then probably XGBoost. If you care about production and real-time scoring, then probably H2O. And I have a lot of repos on GitHub about various things related to gradient boosting machines, which is, by now you see that it's better than deep learning. And I'm almost out of time, so that's pretty much it. Feel free to grab me at the conference or contact me on any of those venues. So thank you so much.
Okay, Szilard, thank you very much for the presentation. I was really shocked to learn your opinion on Spark again. And do we have questions from the audience? There's a question. I'm coming with the microphone.
Yeah, thanks for all this benchmarking. It's really useful, I think. And I was just wondering, have you looked into why some of these algorithms are performing much faster than other implementations?
Yeah, I have some ideas. So the standard thing is that you would think that all these are the same. You take the HashiTip Shirani book, and everyone implements that same algorithm. So you would think that, they must have similar performance. Or even worse, you would think that you can do it, and you start to do your own implementation. No, don't do that. Just use the open source software that many people put a lot of hours into it and a lot of knowledge. And the speed depends mostly on whether you do various optimizations. For example, one that matters the most is how during the algorithm you fetch the data and you keep it into the CPU cache, the L2 cache, as much as possible. So that gives like a 10 times X. Another optimization also, so both of this, they are well discussed in that XGBoost paper that I have the link on in my slides. So the other one is they use the compressed columnar storage, and H2 is using the same. So basically, they arrange the data into columns, and they compress and they sort them. So yeah, there are a lot of optimizations, which is related basically to how CPU and hardware works. And then for the GPU ones, so on GPUs, of course, you saw this not on 10 cores, but on like thousands. And on a lot of data, this will work better. On small data, it will be slower. But GPUs are also great for this kind of optimization. But it really, all this depends on your data. So don't believe anything I said here. Just do it yourself on your own data and see what is the best.
Thank you. Any other question while I'm here? There is one last question on the last end of the room.
So as you see now, we will here talk about TensorFlow. Did you miss it in your benchmarking by accident, or?
I have some benchmark on TensorFlow. So deep learning is really great in other domains like images, speech, and to some extent text analysis. So yeah, I think you should. So basically, this is what you absolutely need to know: some trees like GBM, random forest, linear models, and neural networks. So I think with this 3 or 4, depends how you count them, you are pretty good to go.
All right, thank you very much again for the presentation.